Welcome to podcast number 4, where we're going to discuss the reaction quotient, which is given the symbol of an uppercase Q. Again, if you can calculate the equilibria constant, you can calculate a reaction quotient, but we're also going to talk about what it means in the grand scheme of our things as well. So the reaction quotient is going to help us by helping us determine the direction our reactions are going to go in order for us to reach equilibria. Right? We usually think, okay, we're going to go from our reactants to our products. But if we have a whole bunch of products, maybe we need to go back the other way to reach our equilibrium. And the reaction quotient is going to help us determine that. So again, if we have our general equation, right, our A of A, B of B, and so on there, notice that our reaction quotient is calculated the exact same way as our equilibria constant is. It's just products divided by reactants, just like before. The only difference between calculating Q and calculating K is that Q can be done at any time. K has to be at equilibria and equilibria only. So let's say that we start with only reactants. If we started with only reactants, then our Q would be, all right, partial pressure of C to the C power times the partial pressure of D to the D power over the partial pressure of A to the A power and the partial pressure of B to the B power. Okay, if we only started with reactants, then we would have 0 divided by some number. Well, 0 divided by some number is 0. So our Q was 0. If we start with only products, then Q is going to be equal to some number divided by 0. We don't have any reactants in this case. Well, any number divided by 0 is infinity. And so our Q is infinity in that case. So our Q can go from 0 to infinity. It could be any number in between those two. And in order for us to determine the direction of our reaction, if Q is less than K, our reaction is going to proceed towards producing products. So if Q is less than K, then our reaction proceeds to the right. If Q is greater than K, our Q is going to go back towards making more reactants. And if Q is equal to K, then we're at equilibrium. All right, so the way that I usually think about this is I say, okay, like notice that the caret, right, when Q is less than K, right, the caret is pointing to the left. The reaction goes in the opposite direction as what the caret is there. That's kind of the way that I think about these things. Whatever gets you to be able to do that, because we're going to calculate ones and determine which direction reactions are proceeding. Well, looky here. We're going to do a sample problem where we're going to determine which direction our reaction goes. So we have this reaction of nitrogen dioxides in equilibrium of nitrogen monoxides and oxygens, and we know that K is 0.5. All right. If we have our starting pressures being all equal to 0.1 atmosphere, let's solve for Q and figure out which direction our reaction is going to go. So Q is going to be equal to, all right, the partial pressure of nitrogen monoxide squared times the partial pressure of oxygen divided by the partial pressure of nitrogen dioxide squared. Well, this is going to be then equal to 0.1 squared times 0.1 divided by 0.1 squared. Well, this is equal to 0.1. All right, well, 0.1 is less than 0.5, so Q is less than K, so the reaction will proceed to the right. Continuing with that problem, again, now we have the partial pressure of nitrogen dioxide has a pressure and nitrogen monoxide has a pressure. But notice that it doesn't say anything about the pressure of oxygen. And so if you come to a problem, and the reason that I'm showing this, if you come to a problem and it doesn't state one of the gases specifically, right, then we're going to have to assume that it's not present at all. And so the partial pressure of oxygen is 0. And so again, right, we have Q is the partial pressure of nitrogen monoxide squared times the partial pressure of oxygen divided by the partial pressure of NO2 squared. This is 0.0116 squared times 0 divided by 0.0848 squared. Well, this is going to be equal to 0. And so again, our Q, right, 0 is smaller than 0.5. Our reaction is going to proceed to the right, and that should make sense. Right, we have our two NO2s are going to be coming to equilibria with 2 NOs and oxygens. Okay, well, if there are no oxygens, in order for us to reach equilibria, there has to be some oxygen. And so thus we have to go to the right to make that thing that's missing. All right, that ends our podcast in our reaction quotient. Next, we're going to focus a little bit more in depth on our equilibria partial pressures and calculating them when it seems like we don't have enough information.